Hello students, welcome to Sri Chandra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 3 of a unit alternating current. So let's begin with today's class. In this session, first we are going to see the alternating current through resistance and capacitive circuit, then resistance to inductor, and then series RCL circuits. So let's first begin with the AC alternating current through the RC circuit. C stands for capacitor, R for resistance. So let's have a look. It's an alternating voltage applied to the C and R capacitor and resistance series circuit. So consider a circuit which is having a resistance of R and a capacitor C of is connected in series to a source of alternating supply. This is V is equals to Vm sin omega t. And let's suppose Q is the charge. Q is the charge on the capacitor at any instant t, and I would be the current. I would be the current at that instance. Potential difference across the capacitor at this instant could be Q by C. So let's, since Q by C acts opposite to the applied EMF, the net EMF in the circuit is, it's a Vm sin omega t minus of Q by C, and according to the Ohm's law, this should be equals to IR. So the situation will be, it's an IR that should be is equals to Vm sin omega t minus of Q by C, and let's suppose current I at any instant of time t could be given as, this is equals to I is equals to Im sin omega t plus phi, where Im is the maximum value of the current, and that could be given as, that could be, it's an Im is equals to Vm upon root of under root of r square plus 1 by omega c whole square, or this 1 by omega c that we have seen in the previous lectures, that it would be a xc whole square. It's an capacitive reactance. So this would be the situation. It would be a Vm divided by under root of r square plus xc square, and this is what we call as a Z. It's an impedance. We will see this in detail in the next slides. But first let's focus on this, that we have two relations. The second one, it's an I is equals to Im sin omega t plus y, and this was the first relation, V is equals to Vm sin omega t. That if I observe this two, one of them is the V is equals to Vm sin omega t, and the next is the I is equals to Im sin omega t plus phi. So from equations 1 and 2, we understand that current will lead the voltage by an phase angle of phi. So current will lead and voltage will lag. This could be shown by the phasor diagrams, that if you see this, that current is going to lead, that if I represent Vc over here, if I represent Vc over here and VR over here, because this is the I as well. Yes, so this represents that current is leading the voltage. I hope this is clear. Is it clear? Yes, this can be represented by sinusoidal graphs as well. That how do I define that which one is lead, which one is lag? We have discussed it. We have discussed it that the quantity which becomes maximum first is leading. So look at this. This a red color dotted graph is of the current, and this black color graph is of voltage. So as you can see this, that current becomes maximum at this instant of time and voltage become maximum at this instant of time. So as current has become a maximum before the as current has become the maximum before the voltage, that means current is lagging, current is leading the voltage, or voltage is lagging the current by an angle of phi. I hope this is clear. Is it clear? Is it clear? Now let's see this. Let's see the voltage triangle. That you can see this, that this is VR and this is VC. I have shown it here. It's an I into XC, and this is V. Yes, it is just the addition of this two, which is equals to V is equals to VR plus VC. Is it clear? Is it? Are you sure? Great. Now let's discuss what is impedance. We can say that impedance is the opposition. It is the opposition offered by the CR circuit for the flow of alternating current through it. So I can write it's a Z is equals to Vm by Im, and that should be is equals to root of r square plus 1 by omega c whole square, or 1 by omega c could be said as the under root of r square plus xc square, where Im is the maximum value of the current given as its impedance, and its units and dimensions are same as that of the resistance. So the situation would be something like this, that you have seen the voltage triangle, that this could be VR, this could be the VC, and this could be the V. When I write VR, I can write it's an I into R. When I write VC, it's an I into XC. When I write V, it's an I into Z. From this voltage triangle, from this voltage triangle, I can have this impedance triangle too. It is something like this. Yes, this will represent R, this will represent XC, this will represent Z, and this is the angle, I should say. It's a phase difference between voltage and current. So from here also you can see that Z is equals to root of R square plus XC square. So this is the second approach. This is the second approach to see this. First approach will be using this voltage triangle, or you can say from this phase diagram you can identify that this Z would be equals to root of R square plus XC square. I hope this is clear. Is it clear? So this triangle is what we call as an impedance triangle. This is impedance triangle and play a very vital role. Please do remember this. So if current in the circuit is ahead of EMF by the phase angle, if current in the circuit is ahead of by the phase angle phi, which can be related as it's a 10 phi, that should be is equals to XC by R, and from this it could be written as phi is equals to 10 inverse of XC by R. I hope this is clear. From this I can have one more very important term that could be written as it's a cos phi. What it would be, this will be angle, so cos phi would be equals to R divided by Z. This cos phi is said as the power factor of the circuit. This is what we call as the power factor. Please remember its name, it's a power factor. Yes, we will see the importance of it in the next lectures, but please do remember this, that this is the power factor, and which we call as the cos phi, which is equals to R by Z. Is it clear up till now? Is there everything clear? Are you sure? Are you sure? Do you? Do you? Great. Now let's discuss the alternating current through LR circuits. What we understand is, according to the LR circuit, it's an AC through an inductor L and a resistance R in the circuit. That this is the resistance, and on this we have wounded one coil over a soft iron core. So this will behave as an inductor. So consider a pure inductor of inductance L and a resistor of resistance R. They are connected in series across an EMF, and when they are connected across a series, I could say it's a V is equals to Vm sine omega t, as shown in the figure. So at any instant of time, t, let the current in the circuit will be the I, and the back EMF developed in the inductor will be equals to L di by dt, which will opposes the applied EMF E. So from this, so the effective EMF in the circuit will become V minus L di by dt, and this should be equal to the product of resistance and current, and this will be equals to IR. So that means it's a V minus L di by dt, that would be equals to IR. So this is the case where that AC has been connected with the RL. So in this, applied AC EMF has an instantaneous value of V, which is equals to Vm sine omega t, and from this I could have this relation that V is equals to Vm sine omega t. that is equals to IR plus L di by dt. So current I at any instant of time could be written as, which is I is equals to Im sine omega t minus of phi. And as I have written this is as I is equals to Im sine omega t minus of phi, I could have this kind of diagram for this, that let's suppose this is I, as well as this could be represented as VR, and and this is lagging, this is lagging. So volt, this is y axis, and this is the voltage. It's a, we could say it's a VL, and this has been the phi of this. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Are you sure? Great. So where Im is the maximum value of the current, and the which maximum value of current could be given as this Im is equals to Vm upon under root of R square plus L omega square. Now how this has arrived? It is something like this, that this is the voltage triangle VR, this is the VL. As I see this, that this VL is perpendicular to the VR, so I understand that this phi is equals to 90 degree. And if you want the correct representation of this, then this would be some at somewhere here. This is the line where VL would be there, and this VL, this VR. So this is the situation where V would be there, and this would angle would be the phi. I hope you understand this. This is the situation, that on this axis, oh sorry, on this axis it would be VL, and this would be V. Have you got this? So current is lagging behind the voltage by an angle of phi, and on this voltage triangle it could be seen like this. This is V, this is phi. Yes, I hope this is clear. This is voltage triangle. You should remember this. You should remember this voltage triangle. From this, even an impedance triangle could be formed, and that impedance triangle could be written as this VR, it's equals to I into R, this V, it's an I into Z, this VL, it's an I into XL, and this is the angle phi, which is a phase difference. Phi is the phase difference between voltage and current. So from this I could have this Z, which is equals to root of R square plus XL whole square, and this XL could be written as omega into L. I hope this is clear. So this Im maximum current could be given as, it's a Vm divided by root of R square plus XL square. I hope this is clear. Is it? Is it clear? Do you have any doubts up till now? Is there anything? Is there? No? Great. So the current in the circuit is lagging behind the EMF by an phase angle, that is tan inverse of XL by R. Yes, that we have seen this. It's a tan phi which is equals to XL by R, and here the cos phi power factor would be given as R by Z. Yes, if I draw the sinusoidal diagrams of this two, as in this voltage is leading or current is lagging. When voltage is leading, so voltage should become maximum before current becomes maximum. So you can see this, at this instant of time voltage becomes maximum, and at this instant of time current becomes maximum. So this clearly represents that voltage is leading the current by an angle of phi. I hope this is clear. Is it clear? Is it? Great. Let's see certain quick questions. The EMF and current in a circuit are such that E is equals to E naught sine omega t, and I is equals to I naught sine omega t minus phi. Yes. So here you can see this is the omega t plus 0 degree, something like this, and here it's a current which is equals to omega t minus phi. So as you can see, this current is lagging behind the voltage by an angle of phi. So this AC circuit contains R and C. I hope this is R and L, sorry, my mistake. Is it clear? Okay. Now let's suppose the situation would be that E is equals to E naught sine omega t plus phi, and I is equals to I naught sine omega t, or I should say this, that E is equals to E naught sine omega t, and the current will be equals to, this is equals to I is equals to I naught sine omega t plus phi. This is omega t plus 0 degree. So here it is the case where current leads the voltage, by an angle of phi, and when current leads the voltage, it's having RC circuits. Have you got this? Great. Let's look at this. In an AC circuit, yes, it is the question. In an AC circuit having resistance R and capacitance C, EMF leads the current? No. Current and EMF are in out of phase? No. Both the current and EMF are in phase? No. It's a current leads the EMF? Yes. This would be the correct answer. I hope this is clear. So, are you clear with this circuits? Yes, basically what my motive is that we will see all the circuits first, and then we will switch to the numericals based on this circuits. I hope this is clear. Yes, great. Now let's look at the certain points to remember about RMS values of the AC. So when and when we have been given AC source voltage, that is the RMS voltage, and current in the alternating circuit is always the RMS current. AC emitter and voltmeter reads the RMS value, that means, and when I say RMS value, it is the effective value of alternating current and voltage respectively. AC can be measured by the hot wire ammeters or hot wire voltmeters, that is what we call as the hot wire instruments, because what AC is going to measure, it's an I square RT basically, and this I square R, it's an amount of energy only. Yes, so they are called as the hot wire instruments that can measure the alternating current. And what is RMS? It's a AC produces the same heating effect as that of the DC of magnitude I is equals to IRMS. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Do you have any doubts? Is there anything? Is there? No? Great. Now we have seen two circuits. One is the AC through RL. Another circuit was AC through RC. That means resistance and capacitor, resistance and conductor. Now we are going to see it's an AC through LCR. It's a resistance, capacitance and inductor. Let's have a look that when these three are connected in series, what would be the situation. So in this circuit, AC circuit containing inductance L, capacitance C and resistance R in the series, you can see this is L di by dt, or if current has been passes through this, it's an I by R, or this is Q by C, and the supply has been connected, it's an AC supply which could be given as V is equals to Vm sin omega t. Now let an alternating supply of E is equals to E naught sin omega t or V is equals to Vm sin omega t is being applied to a circuit containing inductance L, resistance R and capacitance C, which are connected in series as shown in the figure. Let's suppose a current has been passed through the circuit and Q be the charge on the capacitor at any instant of time t, and the potential difference Q by C across the capacitor and back EMF due to inductor, that would be equals to L di by dt. So if I apply a KVL on this circuit, I could have this, that total potential total potential on this circuit would be equals to Vm sin omega t minus of L di by dt minus of Q by C. That should be equals to IR. It's a potential drop across the resistance. So according to the Ohm's law, it's an IR which is equals to Vm sin omega t minus of L di by dt minus of Q by C, and this is equals to IR. So from this, it is the situation where L di by dt plus Q by C plus IR is equals to Vm sin omega t. And from this current in the LCR circuit, series circuit, could be given as this is I is equals to Vm by Z sine omega t plus phi. I hope this is clear. Is it clear? Is it clear? Now, the situation would be that you can see this from the phase diagram. This will be the situation that this is the I, or this could be represented as VR, because current and voltage are on the same phase. Current and voltage would be on the same phase when we are considering that it's an resistive circuit. Now now let's see this, that let's suppose this is the VL, and let's suppose this is the VC. So if this is VL, this is VC, and this is VR, we could have V somewhere here, and this would be the angle. I hope this is clear. Yes, do you understand this? In this circuit I have considered that VL is greater than VC. Even it would be the cases, this is the first case. Let's see this. Now if it is the situation where VC is greater than VL, the thing will be something like this, that this is the I, and this would be the VC, and this would be the VL. I hope this is clear. So in this situation, uh, V would be somewhere here, because VC is greater than VL and this is VR. Yes, this is the phase difference between voltage V and current I. So this both could be the situation. But from this, what one thing I am sure is that if I plot the voltage and impedance triangle, it's a voltage and impedance triangle. I could have this, it's a VR. This would be, let's say VL is greater than VC, this would be the VL minus VC, and this would be the V. This angle, it's an phi. So from this I could have this, it's a V which is equals to under root of VR square plus VL minus VC whole square. It has been assumed that VL is greater than VC. And from the same triangle I can switch to the impedance triangle, which will look like this. This is R, this is XL minus XC, and this is the Z. So from this, it's a Z impedance, that should be is equals to root of R square plus XL minus XC whole square. Here it has been assumed that XL is greater than XC. I hope this is clear. So from this I have this, it's I is equals to Vm by Z sine omega t plus minus phi. It's a plus minus phi because we at that point we don't know exactly which one would be at a higher, which one would be at a lower. I hope this is clear. And impedance Z could be given as under root of R square plus XL minus XC whole square. I hope this is clear. Is it clear? Do you have any doubts up till now in this? Do you? Do you have anything? Do you have any doubts? No? Great. Now let's discuss the different cases. That suppose if omega L is greater than omega C, or I should say it's an XL is greater than XC. So this is the case. Basically it's a VL is greater than VC, where we can see this voltage is at here and current is at here, and voltage is leading the current. It is something like this. It's an current I at any instant in the circuit is given as I is equals to Im sine omega t minus phi. And when I say it's an I is equals to Im sine omega t minus phi, in this case, the voltage leads the current. I hope this is clear. Yes, it's a voltage leads the current, or current leads the EMF by an angle of phi. Next case, where XC is greater than XL. When it is the XC which is greater than XL, which is equals to omega L less than 1 by omega C. In this situation, there is the situation where current I at any instant in the circuit, that could be given as it's an I is equals to Im sine omega t plus phi, and which is possible at generally at the low frequencies. So we have plotted the phase diagram as well as this is the situation where we have derived this in the before as well, that this is the VR, this is the I, this would be the VL. If this is VR, this is VL, and this could be the voltage. So from this it could be written it's a VL minus VC plus VR, and this would be the phase difference. Now, and IM is the maximum current that we have shown here. It's an Vm upon under root of R square plus omega L minus 1 by omega C whole square. This is what we call as an impedance, and we have derived also the impedance triangle. It was something like this, that this was phi, this is R, this is XL minus XC, and this is Z. From this it's a 10 phi, which is equals to XL minus XC by R. XL could be represented as omega L, XC could be represented as 1 by omega C, and R is the R. From this it is the cos phi, which could be given as R by Z. This is the cos phi. I hope this is clear. This is the power factor. Do you understand this? Do you? Are you sure? Are you sure? Great. So now let's discuss the third case is, it's a case 3. If XL is equals to XC, what would be the situation? If XL equals to the XC, what would be the situation? That we have the relation that it was something like this, that this is the case when VL is equals to VC, I is equals to Vm by Z, and when it is equals to I is equals to Vm by Z, this is equals to Vm divided by root of R square plus XL minus XC whole square. If XL equals to XC, that means this term has become a 0, and this is equals to Vm by R. If I look at this current, I assume that, and I understand that the this is the maximum current, we have received so far. So this is said to be resonance. Yes, this is what we call as a resonance, that at this instant of time, I am receiving the maximum possible current of this three phases. We discussed three phases. One, let's suppose VL greater than VC, which is the case of the XL greater than XC. Another, it's a VL is less than VC, where VC is greater than VL. And this case, if both are equal, XL equals to XC. So in this situation, this would be the same. It's an XL and XC would be the same. But if they are same, I could identify that if XL equals to XC, when this happens, so let's look at this. It's an XL which is equals to omega L, and it's an XC which is equals to 1 by omega C. From this, it's an omega square which is equals to 1 by L into C. From this, it's a omega square, it's a 2 pi f which is equals to 4 pi f square, it's equals to 1 by LC. So this is f square is equals to 1 by 4 pi square into LC, and from this it is equals to 1 upon 2 pi root of LC. So this is the frequency. This is the frequency of resonance. It is the frequency of resonance. I hope this is clear. Is it clear? Is it clear? You can see this. You can see this from this graph, that let's suppose that at resonance we understood now that omega L is equals to omega C, and from this it's an omega is equals to 1 by under root of LC, and this is FR which is equals to 1 upon 2 pi under root LC. I hope this is clear. Yes. So as you can see, this is the current and this is the frequency. It is a graph showing a frequency versus current. You can see this when resonance occurs. When resonance occurs, this current is having the maximum value of its situation. We have kept a different resistance over different circuits. This is one of the circuit R3, which is having the least resistance, so it is having the maximum current. In the second situation, let's say current has been started from here, and let's suppose this is the zero frequency. As soon as I am moving, as soon as I am moving towards the resonating frequency, you can see this that current starts increasing. Once you reach at this, it's a resonating frequency, your current will become maximum. Again, when you moving away from the resonating frequency, it will start decreasing. So at the frequency of resonance, at the FR, it would be the maximum. It is not the case that you are increasing the frequency, that's why current is increasing. No, 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 it would absolutely incorrect conclusion. So once you are at FR, it will be the maximum. Once you are away from it, the current will be decreased. I hope this is clear. So this is the frequency response curve of LCR circuit, and it just shows that maximum current is there with when it is at resonating frequency. I hope this is clear. So current gain will be the maximum. Current gain will be the maximum when it is the case of resonance. I hope this is clear. Is it clear? Is it clear? So let's discuss something more about the LCR series resonance circuit. So in this case, XL equals to XC, and that means inductive reactance is equals to the capacitive reactance. So if I said XL minus XC equals to 0, that means the reactance is, when we call XL, it's an inductive reactance, and XC it's an capacitive reactance, then the reactance of the circuit is a 0. And when I say a reactance of the circuit is 0, that means now dependency, it's a dependency on frequency is 0, because only the XL and XC were the component which depends on the frequency. That if it was the case of an inductor, then if frequency increases, inductance increases. If it is the case of capacitive inductance, frequency increases, then the capacitive reactance or capacitive inductance will decreases. But here, as XL and XC both are equal, or I should say XL minus XC equals to 0, dependency of frequency is over. So now it is the case when Z is equals to root of R square plus XL minus XC whole square, only the R would be there, and which is not depending on the frequency anywhere. So this is the impedance of the circuit is minimum, and this is equals to the resistance. This is the current where I could say it's an IM, maximum current available, that would be equals to Vm by R. Yes. So this series resonator circuit is also called as the acceptor circuit. One more graph of the resonance circuit is could be written like this. This is the I, and this is the frequency F. As we have already discussed, we are going to discuss again one more time, because this will represent some more information. So look at this. It's an F equals to 0, and as soon as I am switching towards the FR, that my current start increasing. Look at this. It is increasing, 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 increasing. At this point where frequency is FR, I am at the maximum possible current. As soon as I am leaving this, that means still my frequencies are increasing. Still my frequencies are increasing. What I found is that my current starts decreasing, and it is something like that. I hope this is clear. Is it clear? So this kind of circuits are used in the radio and TV, where we receive the desired station by making the frequency of the circuit equal to that of the desired station frequency by varying capacitance, which gives the resonance condition. I don't know whether you have used it or not. It was the previous radio stations, radio units were there. It was a big giant, generally black colored box were there, and on that black colored box, one what we can say, it's a one rotating kind of thing could be there, which is we are rotating in clockwise or in anti-clockwise, and even one what you can say indicator was seen on that, that it's a needle kind of thing which is going to move in positive x and negative x. So what we understand is that we are tuning the station. What if someone asks me that what you are doing with this, that we generally call or we heard the people by saying that we are tuning the station. In actually we are varying the capacitance, because what we are achieving is that, let's suppose we are at here, when we reach here, by trial and error we can have the maximum current, and this maximum current, that means yes, something has been heard from the radio. I hope this is clear and you understand this situation. Is it? Great. So this is what resonating frequency is. Now one more very important thing is that, let's look at this. This is the resonating frequency, but this power or this current, this is the 1 by root 2 times, it's a 1 by root 2 times of the maximum current. And whatever the frequency I received, this is what we called as the lower frequency. Again this is the 1 by root 2 times of I max, it's the upper frequency. The difference of this frequency is bandwidth, which is, in my case, it's an fh minus fl. Or if you talk about the powers at this frequencies, that I current is I max by root 2. When I say it's a power, it would be a I square by r. Oh sorry, it's an I square r, sorry. So P at lower frequency or at higher frequency, this is equals to I square r by 2. So at this point power would be half. It's let's say this is, at this instant power would be the maximum, and at this both the instance power maximum by 2. So we define even the lower frequency and higher frequency something like this, that it is the frequency where power received will be half of the maximum power. That is what we call as the lower frequency, or that is what we call as the upper frequency. I hope this is clear. Is it clear? So now do you understand what bandwidth is? Do you understand what resonance is? Do you understand how resonance can be developed and everything? Do you? Do you have any doubts up till now? Is there anything? Is there? No? Great. Now I would like to plot one more graph, that, let's suppose this was the situation, that this was the current versus omega, or this was the current versus frequency, which we have already plotted. It is something like this. Yes. And this is the resonating frequency where current will be the maximum. Now if I plot the same graph for impedance curves, that this is the z and this is the omega, how it will look like. What we understood is that this z is equals to root of r square plus xl minus xc whole square. Yes. So initially it is, as you can see, this current is at minimum level. So it's an impedance which will be at maximum level. It starts decreasing and it reaches a certain value where it is minimum possible, and at this instant of time it is equals to r, and this is the frequency. It's a resonating frequency. And as we are moving towards the frequency which is separated by a certain distance from the omega r, it will again start increasing. It is something like this. I hope this is clear. Yes, please do remember this. Many of the examinations they have asked this. In many of the examinations they have asked this. I hope this is clear. Is it clear? Are you done with this? Have you? Have you done with this? Do you have any doubts? Do you have any doubts? Are you sure? Are you sure? Great. Now let's discuss something very important about series LCR circuits. The first thing is that we understand that this is V, that should be is equals to V would be equals to Vm sine omega t, and this I, that should be is equals to Im sine omega t plus minus phi. Why I said plus minus phi? That you understand that it is possible that it is increase, that current is leading the voltage, or it is possible that current is lagging the voltage. Now let's discuss that. If it is the case when XL is greater than XC, or I should say it's an VL is greater than VC, then the circuit will be inductive circuit. Then the circuit will be inductive circuit. And when I say circuit will be inductive circuit, when I say circuit will be inductive circuit, who will lead? Who will lag? Tell me. Who will lead? Yes. Who will lead? Did you forget it? Have you? Have you forget it? Great. So circuit will be the inductive circuit, and when circuit is inductive circuit, it is the case when voltage will lead the current. If it is the case when XL is less than XC, so when XL is less than XC, it's a VL is less than VC, and in this situation circuit will be capacitive. Circuit will be capacitive circuit. So in this case current will lead. Current will lead the voltage. And last but not the least, if XL is equals to XC, it is resistive circuit. It is the case of resistive circuit. And if it is the case of the resistive circuit, that means voltage and current are in phase with each other. Do you understand? Yes, great. Now one more thing, that when VL equals to VC, or I should say XL equals to XC, the current will be only the Vm by R. I is equals to Vm by R. I hope this is clear. We have the cos phi, which is equals to R by Z. In this situation, that as you assume that Z is equals to root of R square plus XL minus XC whole square. But as it's an XL equals to XC, so this is the case where Z equals to R, and from this it's a cos phi is equals to R by Z, which is equals to R by R, which is equals to 1. So it's a power factor is a unity, and when I say power factor it's unity, it's a phi is equals to 0 degree, which we have already proved that voltage and current are in phase with each other. I hope this is clear. Is it clear? So do you have any doubts up till now? Do you have any doubts? Are you sure? Are you? So now are you ready for the questions? Yes, we have seen three circuits. One is the pure CR circuit, sorry, capacitor and inductor circuit. Another it's a capacitor and inductor circuits. And the next it's a series RL circuit. So are you clear with this all circuits? Have you? Have you clear with this? Are you sure? So now are you ready for the questions? Let's move on to the questions. Have your pen and paper and you are going to solve it with me. Let's suppose the question says that when, let's say it's a 0.21 Henry inductor and 12 ohm resistance are connected with are connected in series to a 220 volt 50 hertz AC supply. Find current in the circuit find current in the circuit and also the phase angle and also the phase angle between voltage and current supply. So I need to find out the phase difference as well, and I need to find out the current as well. How will I do this? First make a circuit that this was the inductor having 0.21 Henry inductance, and this is the resistance having value of 12 ohm, has been connected with the AC source. Now one very good thing is they have directly given it's a 220 volt and 50 hertz, so I do not need to convert this to an RMS, as they have already given the RMS. If they have not given me the RMS, I need to first convert it and then I can proceed. So now let's begin with the situation that first I need to find out the current, how current will be available. It's a Vm by Z. So the question is how Z will be available. Z will be available by under root of R square plus XL square, that you know. Now to find out this, first I need to work for the XL. So let's work for the XL first. It is the XL which is equals to omega into L, and when I say it's an omega into L, this is equals to 2 pi f into L. So frequency given, frequency would be 50 hertz, so this is equals to 2 into pi into 50 into L. Inductance would be equals to 0.21 Henry. So this is equals to, it's a 21 pi ohm. Now let's try to calculate the Z, which is equals to Z equals to root of R square plus XL square. This is equals to 12 square plus 21 pi whole square. This will give me approximately 67.01 ohm. So this is the Z. Now I can reach to the I, which is equals to Vm by Z. And if I do this, this I is equals to Vm by Z. This is equals to Vm, it's a 220. Z it's the 67.010, which is approximately equals to 3.28 ampere. I hope this is clear. Is it clear? Now what I want the phase angle between the voltage and current. So to find out the phase angle, between the voltage and current, what I can do is that let's have an impedance triangle. This is the situation, or we can also have the phase triangle, a voltage triangle, sorry. It's a VR, it's a VL, and this is the phi, this is the V. Yes, as I can say, it's a VR is equals to I into R. This is the same angle of the current as well. So from this, it's a 10 phi, which is equals to XL by R. We have the XL, we have the value of an XL, which is equals to 21 pi. We have the value of resistance, which is equals to 12. So this is equals to 10 phi. And from this it's a phi, which is equals to 10 inverse of 21 pi divided by 12. This is the phase angle. This is the phase angle between the voltage and current. I hope you got this. Have you? Have you got this? Now, do you have any doubts in this question? Do you? Are you sure? Are you sure? Do you understand this? Have you? Great. So, now ready for the next question? Are you ready? Are you ready for the next question? Are you sure? Great. Let's move on and look at this. Let's say it. The question is about that, let's suppose a 10 microfarad capacitor, a 10 microfarad capacitor is in series with 50 ohm resistor, and this combination is connected to 220 volt, 50 hertz. Find first capacitive reactance, next impedance of the circuit. It's an impedance of circuit, and next current in the circuit, current in the circuit, and next phase difference between voltage and current. So this all are the requirements. This all are the requirements. So let's begin. What have given? They said a 10 microfarad capacitor is there, which is in series with a 50 ohm resistor, and this is combination connected with a 220 volt and 50 hertz. So situation is something like this. This is the capacitor having value of 10 microfarad, which is being connected with the resistance having a value of 50 ohm, and this has been connected with the AC supply. Yes, this has been connected with the AC supply, and this AC supply is the 220 volt on the 50 hertz. This is 220 volt 50 hertz. So when it has been connected with the 220 volt and 50 hertz, First, what I need to find out is the capacitive reactance. So let's work on one by one. It's a xc, which is equals to 1 by omega c, or I should say it's 1 by 2 pi f into c. So this will be equals to 1 upon 2 into pi into frequency. It's a 50 multiplied by capacitance. It's a 10, but it's a microfarad. It's a 10 into 10 to the power minus 6. So if I solve this, it is 318.5. This is the xc. I have done one of the tasks. Next, what I need to do is I need to find out the impedance of the series circuit. It's a z, which is equals to under root of r square plus xc whole square. This is equals to r square. When I say it's an r square, it's a 50 square plus xc square. It's a 318.5 whole square. Solve this and you will get this. It's a 322.40. This is z. Next, current, it's a v by z. V, it's a 220. Z, it's a 322.4. This will give me a 0.68 ampere. I hope this is clear. And last, I need to find out the phase difference between voltage and current. So to find out the phase difference, let's plot the impedance triangle. That this was the phi, this was the r, this was the z, this was the xc. Sorry, this is xc. From this, it was 10 phi, which is equals to xc by r, where phi is the phase difference between voltage and current. So the xc was 318.5. Resistance would be equals to 50. From this it's a phi, that is equals to 10 inverse of 318.5 divided by 5050. This is the phase difference. I hope this is clear. This is clear. Yes. Have you done with this? Are you? Have you done with this? Do you have any difficulties in this? Is there anything? No? So are you ready for the next question? Are you? Great. Let's work for it. The question says that a coil has an inductance of zero point 0.7 Henry and is connected in series with resistance of 220, it's a 220 ohm, when an alternating source of 220 volt at 50 cps. Now what is it? cps, it's a cycles per second. Basically it's a frequency. So it is at 50 cps is applied to it. Find wattless and wattful component of the current. So first let's discuss what is wattless and what is wattful. When I say wattless current, that would be the IRMS sin phi. And when I say it's a wattful current, it's an IRMS cos phi. So are you clear with this, that what less and what is what full? Yes. When and when they say it's a what less, that means it is having IRMS sin phi, and when they say it's a what full, it's an IRMS cos phi. So this is what we required. Let's check what other things has been given. They said that coil is having an inductance of zero point 0.7 Henry, and it has been connected in series with a resistance of 220 ohm. Let's first make the circuit diagram. This is the inductor, this is the resistor. This has been connected with the AC supply, and this AC supply is of, it's a 220 volt and 50 hertz. Inductance it's of zero point 0.7 Henry, and resistance it is of 220 ohm. So this is all they have given. Now what I want the IRMS cos phi and IRMS sin phi. How will I do this? How will I do this? So first thing that I need to calculate is that, let's make the impedance triangle, and from that let's just calculate what is angle phi. So this is phi, this should be the XL, this should be the R, this should be the Z. From this it would be the tan phi, which is equals to XL by R. This XL, which is equals to omega L by R. Omega it's a 2 pi multiplied by frequency has given, it's a 50 multiplied by zero point 0.7, which is 7 by 10, divide by resistance, which is equals to 220. I hope this is clear. Is it clear? So if you try to solve this, this is 2 into pi, it's a 22 by 7 multiplied by 50 into 7 divided by 220 into 10. This 7 has gone. This is the situation where this is 22, this is 10, and this is 52 is 100, this is 10 10 is 100, so this will be equals to 1. So what I receive, it's a 10 phi is equals to 1. And if it is the case when 10 phi is equals to 1, that means it is the case of phi is equals to 45 degree. It's a phase difference between voltage and current, it is of 45 degree. I hope this is clear. Is it clear? Now to find out the IRMS cos phi or IRMS sin phi, I need to calculate the I. So it is the I, or I should say it's an IRMS. This is equals to VRMS by Z. It's an IRMS is equals to VRMS by Z. So to get the value of Z, I should write this. It's a root of R square plus XL square. So let's calculate it. It's a root of R square. When I say it's a root of R square, this is equals to 220 whole square plus XL. When I calculate this XL, this omega L, this is again 220. So this is equals to 220 whole square. It's a 220 into root of 2 ohm. It's a Z. Yes. So from this now, what less component of current, that is equals to IRMS sin phi. So this IRMS, this is VRMS, it's a 220. Z, it's a 220 root of 2 multiplied by sin phi, where phi is the 45 degree that we have done in the previous slide. So if I write it's a phi is equals to 45, it's a sin 45, which is equals to 1 by root 2. This has gone, root to 2, it's a 1 by 2, which is 0.5 ampere. Now let's calculate what full component. It's a what full component of current. It's an IRMS cos phi. So even this IRMS would be equals to 220 by 220 has gone, and it would be a 1 by root 2, multiplied by cos phi. Again it's a 45 degree. Sin phi cos arrays. Sin 45 and cos 45 will be having the same value, and when they are having the same value, it is again going to be 1 by 2, which is equals to zero point 0.5 ampere. I hope this is clear. This is 0.5 ampere. I hope this is clear. Have you done with this? Are you sure? Are you sure? Do you have any doubts? Is there anything up till now? Is there anything? No? Now let's look at the next question. The question says that a series LCR circuit is connected across a source of EMF. E is equals to, it is 10 sine 100 pi t minus of pi by 6, and current from the supply is I is equals to, it's a 2 sine 100 pi t plus pi by 12 ampere. They will ask me that draw the impedance triangle of the circuit. So this is the requirement. How will you do this? Go through the data first. What they have given is that EMF is given. It's a 10 sine 100 pi t minus of pi by 6, and the current is given. It's a 2 sine 100 pi t plus pi by 12. I need to plot the impedance triangle of the circuit. So what I understand is that, let's suppose this is the situation. This is the phi. This is R. Let's call this as an XC minus XL. How could I come to know that XC would be greater than XL? How? Look at this. This is current, and this angle is, the total angle is 100 pi t plus pi by 12. This is 100 pi t minus of pi by 6. So I understand that this angle is greater than this. So current is leading the voltage, and if current is leading the voltage, that means it's a short. XC is greater than XL. If the angles has been reversed, I should write XL minus XC. I hope you clear this. It says that. Now ERMS, this is equals to 10 by root 2. Same way IRMS, that is equals to 2 by root 2. If I find out the Z, if I could get the Z, then Z, that would be equals to ERMS by IIRMS, that is equals to 10 by 2. It's a 10 by root 2 multiplied by 2 by root 2, and this root 2 has gone, and this is equals to 5 ohm. So this Z is equals to 5 ohm. Now let's calculate the phase difference. It's a delta phi, that would be equals to, it was a pi by 12 minus of minus pi by 4, or minus of pi by 6, sorry. So this is equals to pi by 12 plus minus plus pi by 6. So this is equals to pi by 12 plus 2 pi by 12, which is equals to 3 pi by 12, which is equals to pi by 4. I hope this is clear. So now I am having the phase difference, I am having the value. So situation is something like this, that this was Z, this was phi, and this phi was equals to 45 degree. This is XC minus XL, and this is R, and this Z, yes, it's a 5 ohm. So this is equals to 5 ohm. Now I want the value of the R. I want the value of the R, which could be easily calculated. It's equals to Z cos phi. It's a phi into cos 45, which is a 1 by root 2, as well as value of XC minus of XL, which is equals to Z sin phi. Even it is the same, it's a phi into 1 by root 2. So a perfect triangle would be something look like this, that this is phi, this will be the phi, and this will be the 5 by root 2, which is a value of r. This will be the value of 5 by 5 multiplied by root 2, which is xc minus xl, and this is equals to z. That's it. You did it. Great job. I hope this is clear. Is it clear? Is it? Great. So ready for the next question? You are doing pretty good, but make it quick. Time is running high. So let's look at the next question. Let's suppose I have been given a circuit in which resistor is there, inductor is there, and capacitor is there, and and with resistance a voltmeter has been connected. Let's call this as a voltmeter 2, and with inductor and capacitor another voltmeter is connected. Let's call this as a V1, and this has been connected with the supply, and this supply is of 5050 root 2 sine omega t. They said that if if V1 equals to 40 volt, find find reading of find the reading of voltmeter V2. I need to do this. I need to find out the reading of this. So how will I do this? Look at this. This is the RLC circuit, or I should say RLC series circuit. Yes, this is 50 root 2 sine omega t. So if I find out the VRMS value, it is the 50 root 2 divided by root 2, which is equals to 50. And I know that VR, VL and VC, the situation would be something like this, that this is my VR. Let's understand that VL would be greater than VC. So this is the VL and this will be the VC, and this would be probably the V. So from this I could write this. It's a V is equals to root of VR whole square plus VL minus VC whole square. I have been given V, that is of 50. If I square it's a 2500. That would be equals to VR square, that I don't know, it's a V2 square plus VL minus VC whole square. So this is connected across the L and C both. So that means they have given the VL minus VC, which is equals to 40 square. So this V2 square, which is equals to 2500 minus 1600, which is equals to 900. And from this it's a V2 which is equals to 30 volt. I hope you get this. Do you? Have you? Are you sure? Now do you have any doubts? Is it clear? Is it? Are you sure? Great. Does it clear up till now? Does it? Does it clear? Great. Now let's work for the next question. Let's suppose I have been given the question something like this, that it's a 30 ohm and this is the inductor having the 60 ohm. This is the capacitor having the 60 ohm. It's a 200 root 2 sine omega t. So let's suppose the first question is find out current through circuit. This is the question. So let's understand that this is 200 root 2 sine omega t. If I find out the VRMS, this is equals to 200 root 2 by root 2, which is 200 volt. First thing. Second thing, as you observe this very carefully, this is XL and this is XC. So if I calculate the Z to find out the current, I could have it's R square plus XL minus XC whole square. Yes. So XL minus XC whole square both are equal. This Z is equals to R itself. So what I can have, it's an IRMS, which is equals to VRMS divided by, you should write Z or you should write R, both are the same thing. So this is equals to 200 divided by 30. This 2 has gone and it's 20 by 3 ampere. I hope this is clear. Is it clear? Is it? Are you sure? Now, let's suppose if I extend this question, that in the previous question, find out voltage across resistor, inductor, and and capacitor. So this was the circuit. Let me redraw this. This is inductor, this is capacitor, and the supply has been there, and this will be of 200 volt that we have derived. It's a 30, it's a 60, it's a 60. All will be in ohms. Yes. So this is the situation. And the I have calculated the current, which was 20 by 3 ampere. Now what I want a voltage across resistor. That means let's calculate the VR, which is equals to I into R. The I through this circuit, it's a 20 by 3. A resistance, it's a 30 ohm. This is 3 into 10, which is equals to 200 volt. What is VL? It's basically I into XL. This I into XL, this is equals to 20 by 3 multiplied by 60. This is 20 into 20, which is 400 volt. What is VC, which is equals to I into XC? It's a 20 by 3 multiplied by 60, again equals to 400 volt. So from this you might get an idea that this VR is exactly equals to 200 volt, because this VL and this VC is going to be cancelled out. How? Let's have a look. That if you plot the phase diagram of the same, this will be the VR, this will be the VL, this will be the VC. As I understand that VL equals to VC, if I try to find out V, which should be equals to VR square plus VL minus VC whole square. So this and this component is going to be cancelled out, and from this V would be on this line only. I hope this is clear. Even I would be on the same line. I have plotted it on the upper side so that we can differentiate it. It means a phase difference between voltage and current is 0 degree. It's a phase difference. So phase difference between voltage and current in this situation is 0 degree. I hope this is clear. Is it clear? Is it? Are you sure? Great. So now ready for the next question? Are you ready? Let's have a look. The next question, what it is given. Let's suppose they have given that in a series RLC circuit connected with alternating supply of frequency F. Find the value of capacitor if if current leads the voltage. One more thing they have given is that current leads the voltage by an angle of 45 degree. So how will you do this? They said that series RLC circuit is given and that has been connected with a frequency F. You need to find out the value of the capacitor if current leads the voltage. And as I understand that current leads the voltage, this is the case when XC is greater than XL, or we can say it's a VC is greater than VL. So how will you do this? Even one more thing, it's a phase difference between voltage and current is given. It's a 45 degree, or I should say it's a pi by 4. So as I understand that it's a XC is greater than XL, let's plot the impedance triangle. It's a 10 phi. This is equals to XC minus XL. This is R. This is Z. If I write the 10 phi, that would be equals to XC minus of XL divided by R. This phase difference is 45 degree. So it's a 10 45, which is equals to 1 is equals to XC minus of XL divided by R. And from this, it's an XC minus of XL that should be is equals to R. Yes, so from this it's an XC is equals to XL plus R. It's a 1 by omega C is equals to omega L plus R. And from this it's a C which is equals to 1 by omega into bracket omega L plus R. This is the capacitance. If they have given this in the frequency terms, then replace this omega with respect to frequency. It's a 2 pi f, which is equals to 2 pi fl plus R. This is the capacitance. That's it. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you have any doubts? Is there anything? No? Great. Now let's suppose if in the previous question, if in the previous question voltage leads the current by an angle of 45 degree, find value of inductance. How will you do this? So in this situation it is something like this, that this is the situation, this is phi, and in this situation the voltage leads the current, that means VL is greater than VC. This is the situation where this is XL minus XC, this is R, this is Z. So from this it's a 10 phi, which is equals to XL minus of XC divided by R, phi which is equals to 45 degree. So this is 1 is equals to XL minus of XC divided by R, or I should say XL is equals to XC plus R. So from this it's an omega L is equals to 1 by omega C plus R. From this L is equals to 1 by omega C plus R into bracket 1 by omega. I hope this is clear. This is the inductance. Yes. So this impedance triangle has a very critical role in solving the questions, and it helps us a lot to do it quickly. Yes. So always keep this in mind, that this could help us a lot, this could help us a lot, and that is to be used. this is to be used. I hope this is clear. Now let's work for the next question. Let's suppose if someone asks me that a capacitor, a resistor, and 40 millihenry inductor are connected to an AC connected to an AC source of supply, having frequency of 60 hertz, having frequency of 60 hertz. Calculate the capacitance of capacitor if if current is in phase, if current is in phase with the voltage. So if current and voltage are in the same phase, if current and voltage are in the same phase, you need to find out the capacitance of the capacitor. So what does it mean current is in phase with the voltage? Basically what they want that it is a condition, it is a condition of resonance. So when resonance occurs and when resonance achieves, current is in a same phase with the voltage. So if this is the situation where current is in a same phase, current is in a same phase with the voltage, then I can write it's an XL is equals to XC. So this is equals to omega L, this is equals to 1 by omega C. And from this it's an omega square is equals to 1 by LC. From this you can put the value, it's a C is equals to 1 by omega square L. So we are having everything, it's a frequency is given and even the inductance, it's a 40 millihenry, yes it is given. So just put up the value and get the answer, that you will find the answer, it's a 175.7 microfarad. Please do this. I hope this is clear. Is it clear? Is it clear? Great. Now let's work for the next question. Suppose the question is something like this, that they have given the resistor of a 50 ohm, they have given an inductance and inductive reactance is of 100 ohm, they have given the capacitors and it is having the capacitive reactance of 50 ohm, and that has been connected with the AC supply. What they want is that calculate power factor of given circuit. This is the requirement. Now what is power factor? That we have learned this, that this was the phi, this is the XL and XC both are equal. So let's write that it's an XL minus XC, this is R, this is Z. So when I say it's a cos phi, it's the power factor which is equals to R by Z. Now it's a cos phi is equals to R by Z, this is equals to R divided by root of under root of R square plus XL minus XC whole square. So when I write this, it is the R which is equals to 50 ohm divided by root of, it's a 5050 square, plus XL, it's an 100 ohm, XC it's a 50 ohm, so this is 100 minus 50 whole square. This is equals to 50 divided by 50 into root 2. And when this is 50 by 50 root 2, this is equals to cos phi is equals to 1 by root 2. So from this it's a phi. Cos phi is equals to 1 by root 2. This is answer. If they have been asked me that what is the phase difference of this circuit between voltage and current, it would be a 45 degree, and so on. I hope this is clear and you understand this. Do you understand this? Have you? Do you have any doubts up till now? Is there anything? Is there anything? Do you have any doubts? Are you sure? Are you sure? Any doubts up till now? No? Great. Now, let's discuss a very important terminology. One of them, it's a quality factor, generally generally denoted as Q. So, let's write down what quality factor is. That when I say quality factor Q, basically it is a ratio of omega naught L by R, or you can say it's a ratio of the omega naught C by R. So basically it is the ratio. It is the ratio of the XL by R, or we can say it's an XC by R. This is the quality factor, XL by R, or quality factor is equals to XC by R. Now these are the definition formulas. Now let's check out the application formulas. That means when I write Q is equals to XL by R, if I multiply this with I and divide this with I, then this in I into XL, this is equals to VL by VR. Same way, if it is XC by R and I multiply and divide it with I, it's a VC is to VR. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? One more thing is that when I say it's a Q is equals to XC by R or XL by R, or now we have derived one more, it's a VL by R, or it's a VC by VR. In the case of the resonance, in the case of resonance, we understand that VL equals to VC and VR is equals to V supply voltage. So quality factor, but in the case of a resonance, provided resonances happen, could be given as this Q is equals to VL by V. When I say V, I mean V supply, or I should write it's a VC by V. Please note this. This is having a very famous question of the quality factor. So please keep this in mind. Please. And formula of quality factor according to the bandwidth, it's a Q is equals to omega naught divided by 2 into delta omega. While I say delta omega, it was the difference of the frequency. It's an omega high minus omega low. This is the quality factor of the circuit. Please note it down, this formulas. I have written it on the one slide so that you can have a note of this, and we will switch to the questions based on this. Please note this. Have you noted it? Do it quickly. Do it quickly. Have you done it? Have you? Great. Now let's check the question based on this. Let's suppose I have been given a certain circuit. This R, this L, and this C is given. Even this has been given. Yes, supply. So what they have given is that voltage across inductor, it's a 50 volt. Voltage across capacitor, it's a 50 volt. And they have given that supply voltage, it's a 50 volt. Sorry, this is, let's call it, this is 25 volt and 50 hertz. So they said that find out quality factor of of given circuit. So this Q, that is equals to VL by VR, but at the time of resonance, as you can see, this is 50 volt, this is 50 volt, so it is the case of the resonance. So this could be written as it's a VL by V of the supply, or it should be a VC by V of the supply, because at the time of resonance VL and VC would be the equal. So this quality factor would be equals to 50 volt divided by 25, which is equals to 2 volt. Which is equals to 2. Sorry, it's a number. So quality factor of this circuit will be the 2. I hope this is clear. Is it clear? Is it? Now, do you have any doubts over this up till now? Is there anything? No? Great. Now let's discuss the one new circuits, which is a parallel RLC circuit, or it's a parallel. Let's discuss directly the resonance circuit. We will have idea over this too. Let's suppose we have this kind of circuit, that this is a resistance, this is an inductor, this is a capacitor, and this all have been connected with the AC supply, but at this time they are in parallel with it. It's a, let's suppose it's a V is equals to V naught sine omega t. This is inductance L, this is capacitance C. So let's call this current as an IR, let's call this current as an IL, and this current as an IC. I hope this is clear. So this is IR, this is IL, and this is IC. Now one more thing is that this is V is equals to V naught sine omega t, and you can see this supply is in parallel with all this. So basically it is not a new thing for us. It is just a case of the pure capacitive circuit, pure inductive circuit, and pure resistive circuit. It is same thing that we have learned in the previous class. Yes, a pure AC circuits. So this is basically a same thing. They are the pure inductive circuits, pure capacitive circuit, and pure resistive circuit. I hope this is clear. So if I need to plot the formula, and I need to derive all the formulas, and I need to plot the phase diagram of this. How will I do this? How will I do this? What do you think? What I understand is that, let's suppose, call this is the IR, current through resistance, which is same as the V. They are in phase, because in a pure resistive circuit these two are in phase with each other. Now let's suppose it's an IC. As I understand that V and IC is having a phase difference of 90 degree. Yes, so this could be, and I have drawn it on the upward direction because current is leading the voltage, and IL, a current through the inductor, current in the inductor lagging behind the voltage. This is the situation. So if I see only the currents, this is IR, IC, and IL. Let's assume that, let's suppose IC is greater than IL. If this is the situation, then this would be the resulting current I. So from this I could have situation something like this, that this was the IR, and this was the case of the IC minus of IL, and this is the I. So from this it is I, which is equals to under root of IR whole square plus IC minus IL whole square. This is I. I hope this is clear. So let's rewrite this relation and certain other terms too, which is equals to I, that should be is equals to IR whole square plus IC minus IL whole square. So this could be written as V by Z. that is equals to under root of v by r whole square plus it's a v by xc minus v by xl. This is xl whole square. So when I write it's a v by z, this is v could be cancelled and this could be given as 1 by z, that is equals to 1 by root of r square plus it's a 1 by xc minus 1 by xl whole square. This 1 by z, this 1 by z is what we call as an admittance. This is admittance. Sometimes and certain authors denote it with the y. It's an admittance. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. Now, from this diagram, look at this. Look at it very carefully. From this diagram, I can have the phasor diagrams too. That can be represented as, let's suppose, this is the IR. This is, it could be written as IC minus of IL. And from this is the I. This is the phase difference between this. So from this, I could write this. It's a 10 phi is equals to IC minus of IL divided by IR. Or from this I could have the relation that it is something like the impedance triangle. That could be shown something like this. This is phi. This is phi. So it's a 10 phi. What could be given as that this 10 phi, this is equals to v by xc minus v by xl. This is v by r. This is v by z. Yes. So this could be written as, it's a v could be cancelled out, and this is equals to 1 by xc minus 1 by xl divided by 1 by r. I hope this is clear. Is it clear? Is it clear? Are you sure? Now, great. So now let's check the condition for resonance. So it's a 1 by z, which is equals to 1 by r whole square plus 1 by xc minus 1 by xl whole square. So if xc is equals to xl, 1 by z is equals to 1 by r, which means z equals to r. And if this is the situation, then this is the current could be the maximum. So again, this would be the condition of resonance. Generally, this is what we call as a rejector circuit. When you want to reject something, you need to connect them into the parallel. And the series RLC circuit is generally the acceptance circuit. Yes. Now let's discuss how the questions could be formed. Let's suppose the situation is something like this. This is inductor and the resistance has been connected in parallel with it. This has been supply. So they can ask, it's a 4 ampere current has been passing through the inductor, which is, you can call it's an IL. Through inductor, they are assuming that the IR it's a 2 ampere, IL it's a 4 ampere. So they will ask, what is I? Find total current flowing through circuit. How will you do this? From this we have the relation that this I would be equals to under root of IR whole square plus it's an IL minus IC whole square if IL is greater than IC, but here no IC is there. So this is equals to root of root of IR whole square plus IL whole square. This is equals to I. From this, it is IR, which is equals to 4 plus 16. This is root of 20. That means it's a 5 fours. It is 5 into root of 2 ampere. I hope this is clear. Is it clear? Great. Ready for one more question? Let's have a look. Let's suppose the question is that resistance is there, inductor is there, and capacitance is there. Suppose the question is that this is 4 ampere, this is, let's say, 7 ampere, through this it's a 10 ampere, and this is the completion of circuit. This I is required. So again the same question, find out current passing through the circuit. How will you do this? You need to find out the current that is to be passed through the circuit. How could I? So the situation will be something like this, that do not make a mistake that this is 10, this is 7, this is 4. It's a 10 plus 7 plus 4. It's a 21. No, you cannot do this, because this is the alternating current. Each current would be out of phase with certain they are making a certain angle with it, and everything would be there. I hope this is clear. So in this situation, this could be written as it's an IR whole square plus, as IC is greater, IL is lesser, it's an RL and C. So this should be given as this is IR square plus it's an IC minus IL whole square. So that should be is equals to IR, which is equals to 4 square, plus IC, it's a 10 minus 7, this is equals to 3 ampere. So it's a 16 plus 9, which is equals to root of 25, and when it is a root of 25, it's a 5 ampere. This is the current that has been passed through the circuit. I hope this is clear. Is it clear? Is it clear? Now do you have any doubts? Is there anything? Is there? No? Great. So let's wind up this session over here. This was very important topic of the RLC series circuit. This lecture might be very lengthier, but this was requirement of this class. I hope this is clear. So please do as many questions as possible from this part of the alternating current, because this is the heart of the alternating current, where R, L, C are connected in series or they are connected in parallel, and different parameters can be asked. So please do as many questions as possible. Thank you. Have a good day. Take care. Bye.